Well, I would mention a number of the shocking facts that we know, because they have to be faced with that, right? So things related to species extinction and ecological footprints, which are very much linked to society, economics, technology. I think I would like to mention that definitely. I would like to mention how these issues are related to some others, for example, the problem of demography, the problem of migration, and possibly also how we should try to educate people on these insights, because if it's not in the textbooks or in the school, they are not, when they are informed about it, it's too late. I also would like to speak about the scientific background, the machinery which helps us to tackle these issues. So I would like to mention, which didn't discuss, in what sense might evolutionary biology in the next 25 years become deeper than before, right? It's like, you had an idea about the chemical bond in classical chemistry, and at the phenomenological level, you were able to do excellent chemistry. But you didn't understand why the chemical bond and how that is possible. That needed quantum mechanics. It didn't invalidate the concept of valences, but it has made our knowledge considerably deeper. So I would like to tackle a little bit how evolutionary biology might become deeper, not annihilating anything important what we know, but where I see that this deepening might actually happen. And that's the same for ecology, right? And then when you say a few important words about that, you can ask, okay, what does it mean for the past, the present, and the future? The past, does it really help to understand better how we came about? The present, does it help to understand better what, for example, the limits of sustainability are from a biological point of view? About the future, whether we are going to maintain a stable ecosphere, whether in that ecosphere we will be significantly changed by autoevolution, and what would be the impediments, so the problems is progress, so what complications might arise, because those complications is that the young generations need to be tackling with, right, in the future. So I will
what is
autoevolution is you are evolving the human race by artificial intervention. We discussed a number
briefly
of
at the end of yesterday.
Exactly. And then I would ask the question, okay, given all this knowledge that we have and the possible deepening of it, can it shed light on the expectation whether we are alone or not? And that relates to the future. So this is how I would package.
I think what is in my heart to talk about, I was hoping that there'd be a lot of intense discussion where science is going. There's been some discussion of that, but not that much. What I would like to talk about, I think, is where I notice there's two areas interest me. One is algorithms / computation. That's interested me for the last 5 years. Certainly not the economy, as I keep pointing out. God, I hate being labelled. Sorry about all this. What I would like to make some observations, perhaps based a little bit on what was said here about AI, but my observations would be something like this. Where is computation taking us in the sciences? And maybe I could link up. I thought the discussions here, by the way, in the last day or two were really very much on target and very interesting. So I'm not trying to dismiss that, but you asked what is in our hearts. I think that computation, whether it's in what Terry does or in astronomy or anywhere else, is altering our view of how our understanding of how systems work. Systems evolve over time. It's producing novel technologies to probe into huge areas like the brain animal brains and human brains. It's given rise to a subject that I would happily label myself with, and that's complexity science. Complexity science basically hardly exists without computation. And it's given rise to something that I was hoping we would talk about. It's up on the board under complex simulations, but thought experiments, if you like, that are done by computer. I have a very strong feeling, and I gave this as a talk here about a year ago, that we are shifting in science, shifting the basis of how we talk, or the language of science. Just to explain this very quickly, all through the 1600s, in 1600 or so, let's go a little later and take the time of Galileo, 1620s, it was well understood, in fact earlier, Kepler and others, that science or natural philosophy was thought about in geometric terms. By the end of the 1600s, that had begun to shift, in particular with what Newton was able to do, 1686, 87, when the Principia came out. Newton devised much of that using equations and the calculus, which...
It was very interesting if you read the Principia that it was all geometric.
That's right. He went back on his tracks, covered it over, and the exact quote is, he said, I want to present this in good old-fashioned geometry.
You want to make it obscure, you didn't discover it that way.
Well,
you want to make it rigorous.
Yes,
you could say you want to make it acceptable as well. Anyway, we shifted in the 1600s from geometry to an expression that almost thereafter, from the 1700s on roughly, until now, describing everything in equation terms. I believe that certainly since the 1930s, we're also making the slow and steady shift towards re-expressing science in terms of algorithms. And I mentioned this, or gave a talk on this a year ago. If you think in terms of mathematical spaces, everything you can say in equations can be said in geometric terms. If you think in terms of equations, everything you can say in algorithms can be expressed in equation terms. This is basically just standard mathematical thinking. So it's not that one replaces another, but it takes off the constraints. What I would love to mention tomorrow is that I think, if you want one theme that really interests me, I think computation is changing the game completely and utterly. We're shifting towards thinking in algorithmic terms. Algorithms are giving us AI. All these algorithms are enhancing and giving us novel technologies to probe into things. We are able to do thought experiments on the computer, and that's giving us a third channel of science, physical experiments, theory, armchair theory, but also computational experiments. It's giving us much deeper understanding of dynamics, which goes under the heading sometimes of computer science. The theorems that people like Chaitin and Turing came out with, and their subsequent followers, is giving us all of AI, which may change science in 30 years or so. So that's what really interests me. It was touched upon here. You know, this is the basis of the Complexity Hub in Vienna. It's the basis of a lot of thinking, if I'm quite right, that you've probed into. Mm-hmm. It's the basis of the modern, the actual eyes that we can put out into the cosmos or the heavens, and it's the basis of some of these things that are moving forward. In fact, computation and neuroscience have always moved in tandem since the coming of the computer. So I find it fascinating.
So, I love the message. I think it's an important one that needs to be emphasized. And actually, it's related to another message that I think will complement yours, which is I want to focus on information.
Yeah, that's fantastic.
And here's where I see the 21st century. So I actually had to put a lecture together for a popular audience. It was it was called an oration. It was in Melbourne, and it was the Clark oration for Graham Clark had created a cochlear implant.
Mm-hmm.
And so there was like 2,000 people in the audience, and I had just gotten off the airplane, the Qantas airplane from San Diego.
And you had to orate.
And I had to come up with narration, but what I tried to do was to look at what are the hot areas right now in science. Okay, and let's list them.
That's right.
Computer science is hot. I mean, it's just in terms of jobs and impact and so forth. Biology.
Yeah.
Biology is hot in terms of genomics and so forth, and the brain is hot. Okay, what do they have in common? They're all about information.
Yes.
Biological information, how you manipulate information, how the brain represents information, and so I sort of see this as all interrelated. And as we develop algorithms in computer science, we can see how it is reflected in the brain, and I can give examples of that. And so I like the idea, though, that it's a different kind of mathematics from previous ones. And here's another little insight, which we didn't at all talk about here, but I think would be a really useful thing to think about. Even more complex than the brain itself is the fact that there's a construction project that takes you from a single cell to the whole body and brain. That's a development, and that is a hyper problem. And it's amazing. And how do you think about it? I mean, what is our best way of thinking about it? Mathematically or in terms of analogies. It's a little bit like a computer program, right? In other words, things unfold one instruction out at a time. You double the cells at this point, and then you look for signals in your neighborhood. And if you get the signal, you do this, and if you don't, you do that.
It's algorithm.
It's a program. It's an algorithm.
Yeah, absolutely. And then a further question is how this algorithm evolved.
That's
right, because the component mechanisms.
Exactly.
You see, that's a super.
So it actually I think will help us explain how it could possibly have evolved. And the reason is, in a program, you change one little instruction, and you can get a vastly different answer. Right.
Exactly.
And in fact, that's what you need for evolution, because you can't change 100 things at the same time and expect it to work, right? You only change a few things, but they have to have an impact up the road, and it has to be viable impact. So in any case, that's a few ideas I had, but I think what I'm going to say is going to complement exactly what you're saying.
Perhaps I should go first, because yours is very much an instance. Also, I want to throw in one other thing computations caused. Algorithmic information theory. I don't know if you've read much about it, but where something like, how an embryo goes from single cell to being a complete being, a complete organism by birth, is that's thought of as a decompression of the algorithm, if you like. The actual program running. We have an algorithm built in as to how all these cells find the right places, etc. But giving them nutrients, supplying all the parts, the biochemical bits and pieces, that's actually running that algorithm. So there's a lot of insights coming from algorithmic information theory.
It raises a really deep question, which is, what's the minimum amount of information that you need to describe that process? And that is also something in computer science. But there may be things that are so complex that there's no way you can reduce the complexity except running the program.
That's right. Random numbers, for example. That's right. And that's another insight of this sort of theory. I just want to make one other observation, and that is, I hope this doesn't bother Martin too much, but I would say 50 years ago, the classic science, when we think of science, we tended to think of physics and to some degree chemistry, supported by linear and continuous types of mathematics. Now it's shifted, and besides physics, I think that the base classic sciences, when we think of sciences, are biology and computer science, strangely enough. Not yet neurobiology, certainly not economics, thank God. But so, for example, complexity is, if you wanted to, there's many ways to define complexity as a science, but it's a biological way of looking at the world, or you could say a computational way of looking at the world. And so science itself is shifting as both becoming algorithmic and computational based on information theory, and then we're all thinking much more biologically than we used to, because there's all these complicated mechanisms. And at the back of it all, if you peel off those structures, physics.
Well, I mean, first I would emphasize that physics is the simplest science, and although
it doesn't seem
although it underlies all the others, as I explained in my talk yesterday, reductionism isn't true except in some non-useful sense, because each science has its irreducible concepts. But I'm an astronomer, and astronomy is not only based on physics, but is also, in a sense, the grandest environmental science.
Yes.
Because we're observing our cosmic environment, which everyone has looked up at through historic times, and we're now realizing it's very complicated, and we can trace cosmic history back 13.8 billion years to a regime when the physics was so extreme it's unknown. But also, we are finding out that the cosmic environment is more interesting because each star has planets around it, and we now realize that as astronomers we've got to engage with our biological and evolutionary colleagues because we want to know whether in these other planets, which are rather like the Earth, as we can discover already, evolution happens. And this leads to the question of, is simple life widespread? If simple life is widespread, does that mean complex life is ever widespread? How would we detect it? How would we react if we did detect it, etc.? So I would address those questions. I'd also say that the one special perspective which astronomers probably bring compared to most other educated people is an awareness of the vast future. Most people are aware of the 4 billion years of biological evolution and of the Earth's history. Some are aware of the time since the Big Bang, but we are certainly aware that the time lying ahead is at least as long, and that makes us focus on future evolution, post-human evolution.
And the heat death of the universe.
Oh yes, I wanted to
Well,
ask.
yes.
We didn't discuss it yet.
No, we don't. I mean, I think that may never happen. I don't worry about that.
Can we discuss it later a little bit?
Yes, okay. Yeah. But I think technology can deal with that when we get
in the future.
In that next time.
meeting.
And but I've written a bit about that, so I'll tell you about that. But I think the point I would want to make is that we know that the Earth and the Sun are only halfway through their lives, and so the time scale for future evolution here on Earth and away from the Earth is as long as the time it's taken for us to evolve. And then, given that that evolution is going to be, what was the phrase you used? Not
Meta.
Future evolution is going to be
Auto-
not that
auto
evolution. Yes,
yeah.
That's going to be a lot faster, and it'll happen on Earth, and maybe some species or electronic systems would rather be away from the Earth under zero G. Then far more marvelous things will happen in the future. So I would say that we ought to think about us as being a fairly early stage in the emergence of complexity in the universe, not the culmination. But then, having said all that, I would say that even in this perspective, where we look billions of years in the future as well as in the past, this century is special because it is the first when one species, namely ours, can determine the future of the entire biosphere, and it may also signal the transition from organic to electronic intelligence. So it's important for both those reasons. And I would tell young people that they're living through this century, and which scenario emerges will depend on their generation. And I'll say, if they want to be scientists, they should pick a science where new things are happening, new advances happening fast, or new techniques, and above all, they should familiarize themselves with computational techniques because they are taking over. They're crucial in non-experimental sciences like mine, but are taking over even some of the experimental sciences.
I was going to say, you mentioned physics. So I think one of the most exciting things that has happened just recently is gravity waves, right?
Yep.
In other words, the fundamental physics, gravity waves.
Yes,
So physics is alive and well, it's
Yes.
but it's on a grand scale now. It's
Yes.
not-
Well, I mean, of course, we've already seen lots of cosmological explosions, but that's a strong vindication of Einstein's theory. But also, it's an extreme example of how 90% or more is of scientific advances engineering.
Yeah.
Because that is the most amazing engineering achievement.
It took 40 years.
Yes, to measure.
Yeah, 800 million.
Yes, a change in distance of 10 to the minus 21. That's the thickness of a hair at the distance of Alpha Centauri. They measure that, and these two mirrors, 4 kilometers apart, they're displaced by 10 to the minus 16 centimeters, which is 10 to the minus 10 of a fringe of visible light. But that's what they detect.
Where are the mirrors?
I'm nosy.
Well, they've got L-shaped configuration with two mirrors at each end, and they've got similar apparatus 2,000 miles apart in Washington State and Louisiana, looking for coincidences.
Yeah.
And they found a sort of chirp which was indicative of two black holes merging together. They've been looking for this, and it's not a huge surprise. It's a slight surprise that these were two 30 solar mass black holes, but it's a huge. The main point is it's a great technological achievement, and also probably a firmer vindication of Einstein's theory than we had already from.
But you see, what
Yeah.
is exciting to me is the fact that it's opening up a whole new spectrum. It's not like you see a new line, at a given frequency. It's like electromagnetic spectrum, but now in a completely different physical
Yes.
measurements.
Yeah.
And it will give you,
Yes.
I think you were discussing earlier at lunch, which is that once you have a new instrument that gives you new information, it's like a whole new world.
Yes, but I mean, I think it depends. It's not a hugely information-rich thing.
Yes.
And the one thing you can say for sure is that the extraterrestrials won't communicate with gravitational waves. no, because this signal.
Wait a second. You're an expert. You just said something was impossible.
Well, they could, but they'd be foolish to do so. Because this signal corresponds to the amount of energy which is equivalent to annihilating the total mass of 3 stars.
That's true, but
Okay.
if you want to communicate
Yeah.
a long way, maybe that's the way to do it.
Well, but we could detect radio or gamma rays or anything.
Okay, no, I agree. It's just
So you wouldn't
saying, I'm just
communicate
saying that's the beginning of a whole.
No, but it is a new channel.
Yeah. Actually, one of the things about this community, on that paper that came out in Fissure of Letters, there was 1,000 authors.
Yeah.
And it was because they put everybody on it who's even working on it anywhere, because it's a community.
Yes.
So I think that was a good idea.
Yes, well, I mean, so much science is now like that, and it has been recognised. And in the awarding of prizes, it's already got some prizes. It got 2 prizes first, which were very good because it was the 2 big prizes that explicitly recognised groups, Gruber and Breakthrough. And then they got one other one, and if they get the Nobel Prize, that'll be extremely damaging and misleading because giving Nobel Prizes to a few people when it's really a group is not only unfair, but gives the wrong impression of how these science is actually done. And they made mistakes like that over the neutrinos last year, over the accelerating universe and others. So I think these prizes should be given only by prize givers that recognise groups. Otherwise, well, maybe this is the next subject, it's sociology of science, and it's very misleading to highlight individuals.